love to talk more about it. Yeah.
Let's thank the speaker again.
Thank you.
And now we have Jennifer, who has just joined University of Vermont as an assistant professor. She'll be telling us about quantum choreographies. Take it away.
Great. Is working? Sounds like it. Okay. We said in the beginning of this workshop that something like 70% of the people here were relatively new to choreographic programming. I am definitely one of those people. I mostly work in the intersection of programming languages and quantum computing. So in the past, I focused on type systems and compilers and so on. And so this is the point where I tell you that quantum computing is a really exciting, rapidly developing field, and it's going to drastically expand computing capabilities, blah, 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 blah. And I'll get into a little bit of what quantum computing is in a little bit. But one of the main challenges is that our quantum computers of today are very small, among other deficiencies, maybe between 10 to 1,000 quantum bits, qubits per device. And so distributed quantum computing is really gaining popularity as a way to expand that computing power by networking devices together. There are sort of other applications, though. In addition to distributed quantum computers, we might also consider distributed quantum networks more generally, like a big quantum internet that allows for communicating both classical and quantum information across long distances, and for enabling secure communication with quantum cryptography. So I was talking about sort of just the idea of distributed quantum computing with Joe and Chris, my collaborators. And we were looking at a diagram that looks something like this. So this is a circuit representation of a quantum program. And you don't really have to worry about what these different operations are, but it's a very informal. It's very, very similar to those to the timing diagrams that Lindsay was talking about, and so Chris and Joe looked at this and said, "Yeah, this looks like it might be a really good application of choreographic programming." And I said, "Oh, what's that? Never heard of it." So today I am going to try to convince you that, yes, this is actually a really great application of choreographic programming. It's not trivial, though, and it introduces a lot of really interesting design questions due to the constraints of the quantum programming model. And so I'm really interested in feedback into these kinds of constraints and how they show up in different settings. So with that in mind, I'm going to start with a very high-level overview of what is quantum computing, what is distributed quantum computing, and then we'll talk in a little bit more detail about the different design decisions that have come up as we've tried to build this system. And finally, I'll end with a little bit of a teaser towards work in progress for an implementation of quantum choreographies, which we call Choreo. Okay, so main idea of quantum computing is that rather than bits, which for any non-quantum things, I'll sometimes call them classical. So rather than classical bits, 0 and 1, quantum computers deal with superpositions of classical bits, which we call qubits, quantum bits. And so the idea of these superpositions is that this qubit is sort of in both the state 0 and 1 at the same time. And we can manipulate these qubits in a variety of ways. One way is by measuring them. So when you measure a qubit, we're going to collapse the state of that superposition into one of the classical bits, 0 or 1. And this is a probabilistic operation, and the probabilities depend on the state of the qubit, et cetera, et cetera. There's other ways to transform qubits as well, which I'll refer to as unitary gates. We don't have to care about what these are. They're described by a certain class of unitary matrix operations. That's why they're called unitary. But all you need to know is that they transform the state of a qubit without measuring it, without collapsing it. So where quantum computers become really powerful is when you have multiple qubits in a system. So if a single qubit is a superposition of 0 and 1, an n-qubit system is a superposition of all length n bit vectors. So there's sort of like an exponential representation going on here, right? N qubits can somehow talk about 2 to the n different bit vectors, or a superposition of those. And a really important concept when we're talking about multiple qubits is the idea of entanglement. Informally, this just means that 2 qubits are entangled if the state of one depends on the state of the other in some mathematically formal way. And an example of this is what I'll call the Bell state, which is a pair of qubits which may be both the state 0 and they may both be the state 1, but there is no probability of one of them being 0 and one of them being 1. And so if you were to measure the first qubit, for example, and you get a 0, then you automatically know that the second qubit is also a 0, even if you haven't actually looked at it. Okay, so this is quantum computing 101. You passed the class, great. When we talk about distributed quantum computing, we've got all the same ideas, plus we have different physical locations. I'm going to refer to these as actors. And one thing to note about these systems is that the quantum state is global. So in particular, different actors might have entangled qubits together, and so you can't just look at the state of one actor system independently. You have to look at it all in the same context. And so what do we do in a quantum distributed system? Well, we can do 2 things. There's a form of quantum communication, which the only thing you can do is to establish an entangled pair of qubits between 2 distinct actors. And so this idea of entanglement generation is what I want to think about of what quantum communication is. We'll talk a little bit more about this as a design decision, but this is sort of the established primitive of quantum networks. This is like what these networks will provide. And then in addition, we will also allow classical communication, where you can normally send and receive classical data. But of course, those can't be qubits. Those can't be quantum data. Okay, so I want to give, so let's give an example of a distributed quantum protocol. And this example is going to be quantum teleportation, which is sometimes referred to as the hello world of quantum computing. And so the idea here is that Alice is going to start off with a qubit in some state, and by the end of the protocol, we would like Bob to have a qubit in that same state. So what we're not doing is we're not taking the physical particle that represents the state of the qubit and moving it to Bob. We're assuming that these are far away distances. So we need to figure out how to communicate the information of the qubit using a protocol. And so, well, I could write this out as a circuit diagram like I showed on the first slide, but I think what I'm going to do is just show it as a choreography. And so this is syntax in Choreo, which is our work in progress implementation, which is a domain-specific language embedded in Rock. So you can focus in on Rock syntax if you like. So I'm going to write a function teleport that takes in 2 actor names, Alice and Bob, and Q, which is a variable that's going to be located at Alice. And so the first thing that we're going to do is Alice and Bob are going to establish an entangled pair of qubits. And those are called A and B. Then Alice is going to perform some local operations. So I'm just using the syntax for Alice's local operations, and these are quantum operations, right? So we've got some unitary operations that transform qubits. We've got some measurement operations which are going to collapse the state of a qubit, and the output is going to be a classical bit, X and then Z. And then once we have those classical bits, Alice is going to send those to Bob, right? So we've got some classical communication going on. And then finally, Bob is going to do some local operations to his qubit using those classical values. I'm not going to explain why this protocol works, but this is the protocol. Okay. And so as I said, this is often described, like written down in a circuit diagram like this. But of course, this is informal. And so if you wanted to actually program a quantum distributed system or even simulate it, you would write in a process representation. There's been plenty of work in quantum process calculus and things like that. I have some informal syntax here. Well, it's not informal, it's the representation of processes that we have in Choreo. And of course, the challenge of the process representation, as you know, in classical process calculi, is the synchronization of communication primitives. Right. So in this situation, it's very simple. We've got this might be hard to read. I apologize, but we've got we want to establish the entanglement, so the quantum communication, and then we need to synchronize the classical communication as well. So, okay, choreographies to the rescue. These processes are, of course, just the result of endpoint projection of our overall choreography. Okay, great, easy, works out fantastic. Let's talk about some of the sort of challenges and design decisions that have come up when we're thinking about how to design and formalize this language so that endpoint projection is actually safe and correct. So the first thing to note is this idea of quantum communication being entanglement generation. And this is kind of like a weird idea, right? So in classical, you know, in the regular send and receive style, regular COM operation, we have a directed operation. And this entanglement generation, for one, is undirected. And of course, you might ask, well, why don't we just have this quantum teleportation idea as the primitive, right? I just showed that you can communicate quantum states from one actor to another. So like, why isn't that the primitive operation? And the answer is that there are other kinds of high-level communication primitives, or not communication abstractions, like just like applying a distributed gate over multiple actors, for example, that really are based on entanglement generation and not on quantum teleportation. And so really, and also a lot of work on like routing entanglement generation and processes for entanglement generation, those are sort of the foundation of these quantum network systems. So there's some arguments that maybe we want teleportation as an abstraction, but I'm going to make the argument that really it's entanglement generation that is the foundational notion of quantum communication. Another constraint that you might not think about is the use of the difference between quantum data and classical data. So classical data, right, when we can reuse it arbitrarily. So even though you send, even after you send some classical data to Bob, and then you send classical data, you send that same data to Charlie, and then you can still use it to compute things and so on and so forth. That is not the case for quantum data. So there is a principle called the no cloning principle of quantum computing, which says that the state of an arbitrary qubit cannot be cloned or duplicated. And so a consequence of that is that you cannot apply a quantum function to the same qubit twice. In addition, if you measure a qubit, I said that it collapses the state of that qubit, right? So it kind of doesn't make sense to still have that qubit around after you're measuring it. So it's kind of like a use after free type of situation. So the typical way that non-distributed quantum programming languages deal with this, besides ignoring it, but the formal way of dealing with it is to have linear or other substructural type systems for these quantum programming languages. And so this is an important component of our choreographic language, is to layer linear types on top of these choreographic programs. So there's one more point, which is more of a meta-theoretic question about choreography. So in classical choreographies, let's say we have Alice and Bob, which are not blocked on any communications. They can take steps independently. And we know that it's safe in the choreographic model, or at least in like the standard choreographic model, that the processes are independent. So Alice can take a step to A prime, and then Bob can take a step to B prime, and that's going to be the same as if Bob took a step first. In the quantum model, these processes are not independent, right? I said that they share a global state, and so potentially the state so if Alice takes a step first and let's say measures one of their qubits and gets an answer, then the possible step that Bob can do might be different than if Bob had gone first. Okay. So they're not independent. However, don't worry, everything's fine, because even though they're not independent, they're still complement. So there's it is easy to reason that, and it's well known that whether if Alice and Bob operate on separate sets of qubits, which means that there's no communication going on, even if they're entangled, then they can still happen in either order, and you're still going to get an equivalent quantum state. But there's a little subtlety baked in there, which is that this operational semantics for these quantum processes are also probabilistic, right? I said that measurement is probabilistic, so it's going to collapse your state to either 0 or 1 with some probability. And if you've ever worked with a system that has both probabilities and non-determinism before, it is a mess. So it would be really great to not have to do that. And guess what? Don't worry. We can avoid, this probabilistic effect in global state. We can also avoid that. So in fact, quantum programming languages in general tend not to use a probabilistic semantics to reason about their behaviors. They tend to use a different representation called, which are referred to as density matrices or sometimes partial density matrices. And the basic idea is, high-level idea, instead of a probabilistic step relation on quantum states, we have a non-deterministic step relation on what is essentially probability distributions over states. And there's other benefits of this representation as well. So we all sort of win. So by using this representation, okay, now we have a non-deterministic semantics over these probability distributions, but that's all good because non-determinism and other non-determinism is just fine. They go together quite well. Okay. So with all that in mind, I showed you the example of syntax of the choreo language, which is this work in progress that I'm building, also with the help of a grad student, Stephen, who I forget his last name right now. Oh no. What? Stephen Baldowski. Thank you. Yes. And so the layout is as follows. We have a local quantum language that has a linear type system, and we've proved type safety and all of this. And this is embedded in ROC, so these are formally verified proofs. And then we define endpoint projection as a function to a sort of embedded process calculus. And then we also have a kind of an extraction or another compilation layer to netchasm, which is a representation that is more widely accepted by quantum network simulators and potentially real quantum network systems. So I'm very excited about this application. So not only just having a choreographic quantum programming language to do this programming in a safe and secure way, but one thing that I'm really interested in that I would love if anybody else has thoughts on, is the idea of using these choreographies as intermediate representations. And so in the context of choreo, right, I can imagine having a sort of high-level version of the language which has some higher-level communication primitives. So maybe at that level, the communication primitives would include quantum teleportation, but also distributed gates, and so on. And then that can be compiled to a version with the entanglement generation primitive, and then that can be extracted to processes. And I think that each of these different layers enables potentially different kinds of optimizations, whether that's at the application layer, whether that's at the sort of network layer, or at the actually like local process layer. So I'd be really interested if folks have thoughts about that. And with that, I think that's all I have. Thank you all so much.
Thanks. Thank you for the talk, and welcome to the choreographic programming community. It's good to have you here. So I have a noob level question about distributed quantum computing. So you showed this quantum teleportation example, and it seemed like it involved both quantum communication and classical communication, right? So the get entangled pair is kind of the quantum communication is happening there, right? And so I guess my question is it generally true that to do distributed quantum computing, you need both quantum communication and classical communication? Or do people ever have like quantum computers that are connected by a classical network? Like, would there be a reason to just do that? Or you know, would that be useful? And I guess the reason I ask is, you know, I find just classical networks, you know, complicated enough. So, you know, so I guess I'm wondering, is there any reason or advantage to doing it that way? Or do you need to also do quantum networking if you're doing quantum computing?
Yeah, I think there's definitely applications for having quantum computers just connected via classical networks. One application that I am definitely very interested in is hybrid quantum computers, where it's actually not exactly that situation, but you have a quantum computer and you have a classical coprocessor. And the quantum computer will, you know, maybe send instructions or parameters to the quantum computer, and the quantum computer can only send back measurement results. And the interaction between those two can be quite non-trivial. So that's maybe one application of that. But I think that there's also protocols that only use that. I mean, you can think about applications of quantum computers that are just communicating with each other. There's things like circuit cutting. So yeah, absolutely.
We have time for one big question while here sets up, or maybe two small ones.
So I maybe this is the same as Lindsay's question. I'm not entirely sure. But this entanglement primitive seemed kind of magical to me, right? Because suddenly everybody can entangle with everybody without communicating. Is that physically realizable, or is there something else going on under the hood that would be good to model?
Yes, there is an entire network infrastructure that is required in order to enable that get entangled pairs between arbitrary actors. And they need to be, you know, connected in the network and so on and so forth. And so I think that is a really interesting question. It's definitely a very important question for like finding good routes through the network and so on. And there could even, you know, whether choreographies are the right thing to model that, I'd love to like brainstorm about that. But reasoning about that like network layer of establishing entangled pairs, there's a lot going on there. So Robert Rand has some really good work about that. Yeah.
Okay, let's thank Jennifer again.